Namaste. Welcome back to the course on physics of nanomaterials. In the first 8 weeks, we have been emphasizing the importance of nanomaterials. We have seen that there are various types of nanomaterials, and from last week onwards, we have started looking into some of the applications of nanomaterials. These applications range from our daily routinely used devices and in also niche areas. If you look around the nanometers and nanometric sized materials that are called as nanomaterials, we have been continuously seeing that there is one aspect which we always emphasize upon, and that is the surface to volume ratio. And we always say that this is high. What is the meaning of that? So, if you look into the nano sized materials, when we say that surface to volume ratio is high, then it means that most of the particles which constitute a material are near the surface, and when they are near the surface, then what is the advantage? That if there are any reactions or processes which are dependent on the interaction of the incoming reactant with the surface, that means areas where interface between the incoming reactant, if this is the incoming, with the nanomaterial is very important. That means the interfacial reactions are very important, then more are the number of atoms taking part in this reaction, higher would be the response characteristics. And that is why it is very important to have surface to volume ratio high in applications where interface plays a critical role. Otherwise, what will happen if you are talking about a material such as bulk material which has large volume, then what will happen? You will have systems which will form these materials, but the number of atoms which would take part in the interface and interfacial reactions would be much lower in comparison to nano sized materials, and therefore, the response characteristics would be much lower. That aspect, that is surface to volume ratio is high, makes nanomaterials very important in applications such as catalysis, where the reactions at the interface plays a very important role. So, let us start in this week by looking into the use of nanomaterials in catalysis. Catalysis is extremely important in today's world. they are finding applications in areas ranging from the exhaust pipe of your automobiles to chimneys, water treatment to batteries, water splitting to dyes, and so on so forth. So, they have huge amount of applications, and these areas are growing on daily basis. So, there are areas which are unconventional areas such as fuel cells. You have other devices where such catalytic particles are being utilized, and there are applications which require precise sized nanomaterials which are arranged in a given manner. So, it is not that you can pick up nanomaterial and just scatter on the surface and start using them. For example, if you have a surface, then you cannot just put randomly some nanoparticles on the surface and then say that we will have high catalytic response. So, in this case you would like that if there is a surface, then the surface should be covered in a manner so that the maximum coverage is there. Now, we know that two particles can come near to each other, but they cannot hit each other because there is a distance of closest approach. So, they can come near to each other, but they cannot hit each other. But to have the maximum coverage, we must arrange them in a manner that they are covering the whole surface, and that means that they should assemble in a manner which is going to give you the desired output, and that is called assembly. Now, will these particles assemble in any manner, or there is a science behind in which these particles assemble to give a proper area coverage, or there is randomness. So, we will see that many of the systems which are actually used and they have become useful for areas such as catalysis, we are talking about systems which self assemble. But what do we mean by self assembly? So, that concept would also be introduced today, and if the particles are assembling in a given manner, then what is or what are the driving forces that enforce this assembly? That will also be introduced today. Then, once you have the systems where you have the desired coverage of particles which are made to assemble in a given manner, we will start talking about their utilization in the area of catalysis. But what is catalysis? That will also be introduced today, and then we will move on to nano size catalysts, the ways they ensure faster reactions without taking part in the reaction. So, they drive faster reaction. What is this concept? We will talk about that in today's lecture. And finally, we will see two types of catalysts, namely homogeneous catalysts and heterogeneous catalysts. Now, if you look into the systems, even if we talk about, let us say, the crystal lattice, we had seen that when there is a crystal lattice formation, when the atoms are arranging in a given manner such that they have translational and rotational symmetry. Then we had seen that the forces which drive this assembly are the attractive forces and the repulsive forces, which are brought together by the Lennard-Jones 612 potential, and when these attractive forces and repulsive forces optimize, then that is the point the atoms start to occupy. So, that was the formation of lattice. Self assembly is also a very similar concept which is liked by nature, and you will find that nature has large number of examples where self assembly is observed. Self assembly is therefore a process which is spontaneous and leads to the organization of molecules or small subunits into larger but well defined and stable structures through non-covalent interactions such as hydrogen bonding, hydrophobic interactions, or van der Waals forces. So, what is happening? There is no electron transfer taking place between these atoms, and it occurs without external control. So, it is an intrinsic property of the molecules. So, when they are brought together, they inherently arranged in a given manner. So, for example, if you see polymers, what do? You have monomers. When you initiate the process of polymerization, then you have the formation of polymers, which is an ordered array of atoms in the main chain. So, you have ordered array and you can also have side chains, but you have ordered array. So, then they self assemble to give you the polymers. You can also functionalize these molecules to get self assembled functional materials. So, you can actually hydrophobize, or you can ensure that there is some kind of a hydrophilicity process which is modifying the surface of these particles which are formed. Then they can have certain kind of functional groups which are attached to these particles, and then these particles start to arrange in a given manner. As the process is natural, it also results in ordered configuration at equilibrium. So, when you have an equilibrium state, you will see an ordered arrangement, and it includes the inbuilt error correction mechanisms. So, even if there is some kind of a fault or defect or misaligned components, then when the particles are growing, such kind of errors are self corrected during the growth of such assembled particles. So, the nature actually drives this process and also gives you the capacity to self correct, and that is being exploited to make synthetically self assembled structures which can then be used. So, you are trying to mimic nature. What is the importance? So, it actually gives you a capacity to simulate structures which are naturally occurring. So, you can understand why certain naturally occurring self assembled systems, for example, proteins which fold into exact shapes to function as enzymes, have certain behavior. So, you can actually simulate such structures, and by studying those structures you can then back calculate or estimate what would be the response characteristics of naturally occurring proteins. You can also then investigate and understand the behavior of DNA strands which pair up perfectly to form a double helix. So, you can find that they actually self assemble to give you a double helix. Even viruses build their protective shells through self assembled proteins. So, viruses cover themselves with self assembled proteins and then they move. Now, if you look into the self assembly, then you will find these highly ordered structures are also quite small. They are in the nanometric range. But now, if you can obtain such structures in lab and you can understand their properties, how their properties can be modulated, how new properties can be induced in them, how you can modulate or modify their interactions with other surfaces, then they can be used in niche areas such as targeted drug delivery, biosensors, or even nano devices for health, medical or energy applications, to name a few. If you look into the types of self assembly, you have various types of self assembly. Let us discuss some of them. You have static self assembly. It happens when molecules arrange spontaneously into a stable final structure. And once formed, the structure does not change with time unless there are external parameters which are used to modulate their structures, such as crystals. This is what we have seen. So, in crystals, if you have, for example, a lattice which is made up of unit cells. So, this is one particles unit cell, then you have another molecules unit cell, and then they are arranged. Now, you have large number of systems which are arranged. So, these atoms are arranged. Unless you enforce some change in them by varying typically thermodynamical parameters such as temperature, pressure, then they remain stable in their original state. They only get to transform to a new structure or a new atomic arrangement when, for example, you change temperature or you change pressure predominantly. Then what do you call? You say that the structure has changed and you observe a phase transition, because you had the condition which led to the modifications in the way the atoms were arranging themselves. So, you find that the nature of lattice changes when there is a phase transition. But if you do not change these thermodynamical parameters, you have a material which has been formed and is kept like that, and you do not change the external parameters. Do you see a phase transition? You do not see a phase transition, you see a crystal remaining a crystal and nothing happens to it. So, these kind of systems are very stable and the structure remains so if there are no external forces. Similarly, you can see the example of DNA double helix, which is a complementary base pairs assembled into a stable structure. So, when you have static self assembly, you do not need to continuously supply energy. They are primarily driven by thermodynamics, and once they are formed, they remain stable. So, this is something which we have been studying in various subjects. So, this is another way of talking about the formation of lattices or stable structures where atoms or molecules are assembled in a given manner. You can have dynamic self assembly. As the name suggests, unlike static, these structures only will exist when the energy is supplied. So, they are not permanent, they are constantly rearranging, and you find them in this state where the condition is far away from the equilibrium condition. This is far away. So, these are examples like cytoskeleton inside cells, where the actin filaments and microtubules assemble, deassemble continuously using ATP. So, you require continuous input of energy, which can be light, which can be ATP, which can be electric field or anything similar which can supply energy. Now, you can ask a question, which one is important? Should you always have a static type self assembly, or you should have dynamic type self assembly, or what else? Actually, both are important. Why? Because if you have static systems, then they give you the capacity to have predictability and stability over time. But if you have a dynamic system, it gives you the advantage of adaptability and responsiveness. So, how fast you can respond to a dynamically changing surrounding, that can only happen when you have a system which itself is dynamic and can respond quickly to a dynamic surrounding. That means, it can adapt to any situation in which it is kept. And hence, it is not about which of them are important, it is only that together when you look into these two assembly processes, then only you get an overview of the way the living and non-living systems organize themselves. As I said in the introduction of this lecture, why should these molecules or particles assemble? These are driven by forces such as the electrostatic interactions between the charges which are being arranged in a given manner. So, you have a positive charge and a negative charge. So, an electropositive atom and an electronegative atom, which attract and then form a molecule, obtain the condition of charge neutrality, and then they give you a stable molecule. So, first they will get attracted towards each other, and when they come near each other, then there is a distance of closest approach and you cannot cross that. So, then you are repelled and then there is a competition, and finally, they can reach to an optimum distance where these forces equilibrate and you have a stable molecule arrangement. For example, if you look into DNA, you have negatively charged phosphate groups which interact with positively charged proteins, and then the overall charge becomes 0. So, what happens when you talk in terms of self assembly? It is the electrostatics which hold the different building blocks together while preventing aggregation. Then you have hydrogen bonding. This will happen when an hydrogen atom is covalently attached to a electronegative atom like oxygen, nitrogen or fluorine, and this interacts with another electronegative atom. These are highly directional and they give you molecules of specific shapes. Again, if you see DNA base pairs, you can have AT or GC pairs, which are stabilized by hydrogen bonds, and you have structurally stable self assembled systems. Then you can have hydrophobic effects. Hydrophobic, that means water fearing. Hydrophobic, so you have water fearing parts of the molecule, and those are non-polar clusters which are there and they like to avoid water. This drives the formation of micelles, lipid bilayers or even membranes. So, you can have examples like lipid tails which have an hydrophobic side inside, and while the heads are hydrophilic which face the water. So, they have the affinity, and in such systems you have the heads as hydrophilic while the tails as hydrophobic sides. So, they are important for biological self assembly and they are utilized to investigate why membranes and proteins adopt certain shape. You can have pi-pi stacking, you can have the aromatic interactions where the aromatic rings tend to stack face to face like coins, and here you can take examples like DNA interacting with some protein side chains, and you can get various types of interactions. Although they are weaker than hydrogen bonding, the pi-pi stacking helps to align the molecules in precise arrangement. Then you have the van der Waals forces. As you know, they are very weak attractions between molecules due to the temporary charge fluctuations. So, they are short range, but very important when atoms are close together. And such examples are seen in cases like amino acids, which can have the hydrophobic sides of the chain coming very close. Then these forces help the packing of these amino acids tightly inside the protein core, and they act as fine tuning glue in the process of self assembly and leading to stabilization of the final structures. So, if you look into various forces, electrostatic, hydrogen bonding, hydrophobic effect, pi-pi stacking and van der Waals forces, they are driving your self assembly, and you have various associated nature of interaction in all these cases which we have already discussed. So, this is just a summary of what we have discussed till now. So, now we understand what are the processes which will lead to formation of stable materials, which are assembling in a given manner. So, let us start using them in one of these applications such as catalysis, where the surface to volume ratio plays a critical role. Now, catalysis refers to a process where the rate or speed of chemical reaction is changed by adding substances which are called as catalysts. Usually, the reactions which we talk about are made faster, but there are very rare cases where a catalyst can also slow down the reaction, and then they are called as inhibitors. And if you do not use catalyst, many essential reactions would be too slow to actually become of any use. For example, if you want to break hydrogen peroxide without catalyst, it is an extremely slow process, but with the use of manganese oxide particles as catalyst, it becomes a very fast process. So, in biology, you have catalysts which are made up of enzymes. You have catalysts which are used in various industries, and these include metals, acids, oxides and their hybrids. So, you have various types of examples. If you look into the catalysts, they actually ensure that whatever they are contributing it, they are actually only having a temporary role and taking part in a temporary interaction. So, they form only short lived intermediates with reactants, and they are not part of the final product. So, if you have an acid catalyst, then you will find here hydrogen may attach to a molecule to make it more reactive, and then finally it gets detached later and does not chemically bound to the final product. So, there is not that hydrogen is chemically binding with the final product. So, this temporary handshake speeds up the bond breaking or forming process. Now, catalysts also provide alternative pathways where they can reduce the activation barriers, and you can have cases where you can also get alternate pathways for undergoing a given reaction, and these alternate pathways can occur even at lower energies. Now, this lowering of activation energy helps in carrying out the reactions at the temperatures which are lower than the normally required temperatures. That means, you can carry out reactions at lower temperatures, meaning with lower thermal energies. So, you can work with lower thermal energies, and you have the same effects. So, you reduce the requirement of energy. You can have two types of catalysts, homogeneous or heterogeneous. If you talk about homogeneous catalysts, then these exist in the same physical state, that is the phase, as the reactants. So, they are either in both liquid phase or both are in gas phase. Now, if you see this condition, that means they are sharing the same medium. You can have high order of mixing and higher interactions. That is why they are called as homogeneous catalysts. Now, these catalysts interacts directly with the reactants at the molecular level, and because of this homogeneous distribution, the reaction is occurring throughout the phase and hence they are faster and quite selectively. For example, you can have alcohol or carbolic acid giving you a ester, and you are adding H2SO4 in solution to catalyze this process, and here both acid and reactants are in the liquid phase. So, you had homogeneous. In heterogeneous, this would be very simple. The catalyst and the reactants would be in the different phases. For example, you can have solid catalyst with gas or solid catalyst with liquid reactants, and they do not occur in bulk, but at the surface of the catalyst. So, these are surface mechanisms, and you can see once the reactants approach the catalyst surface, they are adsorbed, not absorbed, adsorbed onto the specific active sites. Now, bonds in the reactants weaken and reaction proceeds, and products are dissolved, leaving the surface ready for next cycle, and hence they are often called as adsorption desorption reaction mechanism. So, if you compare homogeneous and heterogeneous catalysts, you can easily differentiate between the two, or you can compare them. In homogeneous catalysts, you have same phase, in heterogeneous different phase. Homogeneity is required for homogeneous catalysts to take place, but in heterogeneous catalysts utilization, the reactions are mostly surface driven. You have high selectivity and control in homogeneous catalysts, while it is less selective and may produce side reactions when you are having heterogeneous catalysts. And we have discussed other details already. So, this is the summary table explaining your homogeneous catalysts and heterogeneous catalysts. So, I hope you have understood the basics of self assembly, why are they important, and how such materials are mimicking nature and giving us the capacity to understand various natural processes and also allowing us to design new processes where the reaction kinetics are faster and selective, or they are adaptive to any dynamically changing situations, and hence catalytic nanoparticles have become a very important area of applications of nanomaterials. So, these are some more references which would give you even more details than what I have discussed today in the area of catalysis and the use of nanoparticles in the process of catalysis. So, I thank you for attending lecture 1 of week 9. Thank you.